Continuing on with orientation controls. Now let us think about angularity, which is an angle that's not parallel or perpendicular. And remember that we always need at least one datum with any of these orientation controls. Here's an angularity control applied to this sloping surface. Relative to datum A, there's datum surface A identified on your drawing. This drawing right here is very similar to the one you're going to be drawing for today's assignment. The numbers are a little bit different, but it's really close. Notice that the angle is a basic dimension. Remember that geometric tolerances and basic dimensions travel in pairs. And here's the thinking about that. This basic 30 degrees is a theoretically exact angle. That is the angle this surface would be if you could make a perfect part. Then this geometric tolerance is how much variation you can tolerate away from that theoretically exact angle. This is an angularity on a flat surface, and so this is saying the tolerance zone is two parallel planes 9/1000ths of an inch apart, within which the bumps of the surface must lie. Here's a part where we're controlling the angularity of the center axis of a hole. And again, notice that the angle dimension on that center axis is a basic 60. Basic dimensions and geometric tolerances travel in pairs. So if you could make a perfect part with a perfect hole location, here in the bottom picture is where the hole center line would lie, and this drinking straw, this cylindrical tolerance zone, is centered around that theoretically exact axis location. You can apply angularity to a surface, as you see in this top part, and on the left in the bottom part, and you can apply angularity to an axis of a hole or a pin, and you can apply it to a center plane of a flat thing. Let's think about how we specify the tolerance on an angle. One way is just to specify the angle tolerance, and we have that on our title block in our drawing. Down here in our title block it says, unless otherwise specified, the linear tolerance is plus or minus something. The angular tolerance is plus or minus half a degree. That's what we're saying on our title block. You might work for a company where that's a different number. That's what we're saying. Okay, so unless we say otherwise, when we put an angle on our drawing, the tolerance is plus or minus half a degree. What does that mean? It means that you have a fan-shaped tolerance zone, a wedge shape or triangular shaped tolerance zone. And the farther you get out away from the vertex, the farther apart those lines are. If you were to use your trig skills and just figure out, okay, if this side of this slopey thing here were, let's say, 10 inches long, you would find out that the tolerance zone at 10 inches out there would be over 170 thousandths of an inch wide, almost 3/16 of an inch. That's kind of a lot. So that's a problem for angular tolerances when we do not use GDT. We have fan-shaped tolerance zones. We might be out just a little bit when we're looking at the short distance. We might be out quite a whole lot when we're looking at the long distance. But with GDT, we say there's a tolerance zone and it stays the same size throughout the part. This block here has angularity applied to this sloping surface. And it says, this is a metric part, it says there are two parallel planes 0.4 of a millimeter apart. Here they are in the picture, within which all the bumps on the surface must lie. No matter how long or how short that surface is, there are two parallel planes that are 0.4 apart. That's where the surface has to lie. When you're applying angularity to a surface, you apply your feature control frame any way you want to that says surface. So here they've applied it by using a leader line pointing at an extension line that extends the surface. You could also have a leader line pointing right at the surface, and I think we saw one earlier. Let me back up. Where was it? I thought we saw one earlier. Well, I won't. That was stuck directly to the surface. You can also apply angularity to the center axis of a hole, as we were mentioning. So that's a feature of size. You are talking about the axis of the feature of size. That means your feature control frame, with the tolerance in it, has to be connected to the feature of size dimension somehow. Here they have stuck it right under the feature of size dimension. This one, this is metric again, has a tolerance zone that's a diameter of 0.2 of a millimeter. So here in the picture at the bottom, there's our drinking straw. There's our cylindrical tolerance zone. It's 0.2 in diameter. And however you make your hole in the actual part, it's fine as long as the axis of the actual hole lands inside that tolerance zone. Here's another one. Different numbers, same idea. Here's the tolerance zone. Again, we're controlling the axis of a hole, so the tolerance zone is a cylinder, the drinking straw. We already looked at that. Now, just a couple of comments, or one comment, I suppose. One comment about what your inspector does when you put datums on the part. Here is a part that's very much like the part you will be dimensioning in your drawing today, and it has one datum called out, datum surface A. That means that your inspector can only use surface A as a datum simulator. They are not allowed to rest any other edge or surface against any other datum simulator. They can only set the thing on surface A. And what this picture is trying to say is that means this part can wiggle around, kind of swing around. There's nothing that's going to hold it square and level. By the way, this measuring tool here is called a sine bar. We'll look at that in just a minute. So our inspector has set our part on a sine bar and is going to check the top surface with a dial indicator by running it back and forth. All the bumps on that surface have to lie within two parallel planes that are 9/1000ths of an inch apart. But we've only got one datum. Here's what happens if you give them two datums, A on the bottom surface, and then datum B is that back surface. Now your inspector is allowed to put surface A on the sine bar and rest surface B against some other precision square thing. So it's much more precise. Here's how a sine bar works. This is kind of a dorky drawing, sorry about that. These are metal parts that are machined to a very close tolerance. These are cylindrical pins, and a standard sine bar has these pins 5 inches apart, center to center. There are other sizes, but almost all of them are 5. Okay, so if you have ever studied trigonometry, and maybe you haven't, if you haven't, that's okay. If you have, you will remember that the equation for sine is opposite over hypotenuse. If you're trying to find the opposite and you know the hypotenuse, you can use that formula. Or if you know the opposite and the hypotenuse, you can use them to find the angle. Well, what we know in the case of this sine bar, where the cylinders are 5 inches apart to a very close tolerance, we know the hypotenuse. And if we figure out how high the opposite side should be, if this were a perfect part, we could then stack up gauge blocks to be that height, and then we set our part on this sloping sine bar. That top surface, let me back up here, that top surface now should be perfectly level if by some miracle this were a perfect part, which it can't be. And that's how your inspector checks. So here's a photograph of a sine bar set up on some gauge blocks and our slopey part that's about to be inspected with a dial indicator. You can also use a sine bar to inspect the angularity of the center axis of a hole. That's what this setup is. So they have set the block with a hole on the sine bar. The sine bar is resting on these gauge blocks at a particular height, and they are using a precise gauge pin to stand in for the center axis of that hole. And now they run a dial indicator over that gauge pin. That's how inspection of this thing would work.